tomorrow. There will be lab tomorrow, but you don't have to go. I mean, that's just an opportunity for you to go. It's probably not a bad idea for you to go and start studying for lab 0 and B start doing lab 1. I've opened up both labs. You can start doing lab 1. Lab 1 is basically a graph algorithm that you do in C. So you're going to do it in C without any help of the standard template library. So you can do that certainly after today's class, because I'll teach you Malik. So those things can get going. Office hours are going now. I think that's about the only announcement I have. All right. So let's lecture. I guess it is. It's started already. Thanks. Yep, absolutely. All right. All right. Going to look at a program. So we're going to start. Today I'm going to talk about pointers, okay, which I know is everyone's favorite topic. But hopefully by the end of this class, you will not be afraid of pointers anymore. Or certainly you will have had enough experience with them. Okay, so I got a program over here on that side, which I feel compelled to walk over to, so I'll go ahead and put it on this side. Okay. And before I talk about the program, let's talk about what a pointer is. So memory, when you start a program up, it gets memory, okay? Where does it get it from? The operating system. I mean, it's memory that's on my machine, but the operating system is what gives you access to memory. The operating system gives you a view of memory that doesn't really exist, but it's a nice view because it makes your life easier as a programmer. And what that view is memory is this giant array of bytes. It's either 2 to the 32 in size or 2 to the 64 in size, depending on your machine. Our machine's is 2 to the 64. Okay? And you can access it on a byte level. So you can access it by index. So you can treat this memory array as a giant char star array of chars, right, of bytes. And all a pointer is just an index into that array. Okay? So if the pointer is 0, it's going to get the very first byte of memory. Right? If the pointer is 1,000, it's going to get the 1,000th byte of memory. 1,001 because life's 0 indexed. Now what makes it a little confusing is that my computer does not have 2 to the 64 bytes of memory. No one's does, right? That's a very big number. Okay? So that view of memory is a virtual view of memory. That's not really memory. The way that gets presented to you is that very large regions of this memory array don't exist, and if you try to access them, you get a segmentation violation. Okay? So what's going on underneath the hood is you issue a memory address that you want to do something with, and then the hardware goes through several layers of interpreting that address, right? It'll first look and say, hey, it's in cache. And if it is in cache, I'm going to grab it from cache. And then it'll say, if it's not in cache, now let me see if it actually exists. And if it does exist, then it's in memory, I'll go find it. But at every stage along there, the hardware will be able to check and say, is this an illegal memory address? And if it does, it throws to the operating system and says this is an illegal memory address. And then the operating system gives you a seg fault. That's how that happens, okay? And what's interesting is, potentially you'll learn more about this in 361. All of that, when it goes through the fast path, doesn't touch the operating system. Actually, with the fast path, it doesn't even touch memory. It just touches the cache. But the operating system is involved in setting it up for you, but when things work normally, the operating system isn't even running. It's just sitting there in the background waiting for something to go wrong. It's when things go wrong that the operating system gets involved, or when you request the operating system to do something. We'll get to that. But anyway, that's what a pointer is. It's a very simple thing. It's just a number. It's an index. It's just a scary number because it's a number between 0 and 2 to the 64. Yes?
Why does it bother showing it to you if it's not accessible?
What does it bother showing it to you?
Yeah, why do you have like a bunch of addresses that like you can't
Oh, that's actually a very good question. I've never been asked that question before. Well, one, in a language like C, you can do anything you want. right? So C, you can say, give me this address. So you're going to get that. C++, same thing, right? There are and if you're going to be writing systems code, right, code that's low-level code that's going to be dealing with bytes, bits, maybe a microcontroller dealing with circuits and pins, it's unavoidable for you to be able to ask, hey, what's a legal memory address? Like, you only show me legal ones. In higher level programming languages, you that can be abstracted away from you. Now, again, not in C, not in C++. Python, I don't know Python. I don't know. It may or may not. Interestingly enough, in the 1980s, back when Xerox was actually a computer company and not just a copier company, they wrote a programming language, operating system, and runtime based on the principle that you are not, it won't give you an address you can't use. And because of that, you didn't have to have hardware protection, right? I mean, it had a lot of really good properties, but actually everyone ran in the same space. So I actually theoretically had access to your memory, which I don't in the world we're in now because my memory is managed by the operating system. But in Xerox's thing, there was that. So if the processor wanted to switch from my program to your program, it cost nothing. Very interesting. Xerox did fantastic groundbreaking work in the 1980s, right? And then they decided to become a copier company and let Steve Jobs go to Apple. So, although that wasn't his job. Anyway, it's a good question. All right, so here's now a pointer, again, it's a number. It's just a 4-byte or 8-byte number, again, depending on your size. In our machines, it's an 8-byte number. So here's a program, right? My program's got, well, if we look at it, it's got 4 bytes for the integer. It's got 14 bytes for that character array, right? J is kind of a weird concept. When I use J, I'm going to be given a pointer to the first of those 14 bytes. And now I got a pointer to an integer and a pointer to a character. Those are both 8 bytes. So if I say how much memory is this program using as local memory, the answer is, well, 4 plus 14 is 18, plus 16 is 34. Right. So that's how many bytes there are. Now, when I said IP to I, right, I has 4 bytes. It's sitting there in that giant memory array. It's consuming 4 bytes. When I say IP equals ampersand I, I'm just getting an integer. Where is it in the big memory array? Okay. When I do it with an array, this gives me this. So I don't do an ampersand with the array because J is a pointer to the first thing, even though it's not a pointer that consumes memory. The compiler makes it so it's always pointed to that first byte of the array. So now I've got a pointer to the first byte of the array. Okay? And now if I print them out, I can print them out. They're numbers, right? I'll print them out. I'll print it, and I'll print them in hex because they're big numbers, and the hex makes sense. I know I don't know if you hate hex or not. Most people hate hex. But hex, the thing about hex is, don't try to convert it to decimal. Just let it exist as hex, right? And if it doesn't have any meaning to you, that's fine, it's hex. But there is meaning in the hex, whereas there's not meaning in the decimal number. Okay, so when we compile this, it's probably already compiled, there we go. We compile it, we get a warning, ignore it for now, I'll talk about the warning later. Okay, but when I run it, put a higher on the screen for you, okay? You get something like this, which is the stuff you hate, right? You get the hex. So there it is in my giant memory array. That's where I is, all the way down there at 0x7, whatever, right? And J is real close to it. Look, J is 10 bytes after it, right? So that's what it's weird. 10 bytes? Why is it 10 bytes? There are only 4 bytes there. I don't know. The compiler did it, right? The compiler's the one that did it. Now, interesting things about the hex that you can tell. Supposed to get this later in the lecture, but I'll do it now. Every data type should be aligned on its size boundary. Now remember, I told you the data types. There's 7 of them, right? Chars don't have to have alignment because they're single bytes. Shorts, they have to be aligned on a 2-byte boundary, meaning any address of a short needs to be an even number. Okay, int needs to be a multiple of 4. Double needs to be a multiple of 8. Pointer needs to be a multiple of 8. Where it resides, not this value, right? This is pointing to an int, so you'll note it's a multiple of 4. How can I tell that? Well, the hex makes it real easy for me to tell whether it's a multiple of 4. Whereas the char pointer's not. 10's not a multiple of 4. Some machines it will be. I can tell you, if you go onto like an Ubuntu machine, there's probably a really good chance that's going to be a multiple of 8. Okay. But that's always something to keep in mind. And that's one of the things that the hex gives you, is the hex gives you the ability to know, A, that's a big ass number, right? Sometimes that's just useful to know that this is a big old number. B, it's multiple of 4. It's multiple of 16 here. You know, that's not a multiple of 4. Sometimes that's a big clue to finding a bug. It's just looking at that hex. Okay. If you're on a 32-bit machine, then this number will be more manageable. It's still icky, but it'll be 8 characters rather than 16, which is nice. So if you're on a Pi 3, if it still works, it'll be smaller. I have an example of that in the lecture notes. Okay. Typecasting. So, when you do an assignment like this, of a variable of one type to another type, you have to think to yourself what's going on. Okay? So, what is going on? This, believe it or not, is an int. Okay? So I'm taking an int and putting it into a char. Right? This is a char, which I'm putting into an int. And this is an int, which I'm putting into a float. Okay? So you got to think what's going on in all these circumstances. Here what's going on is I actually drop the first 3 bytes, and I just take the last byte, which is A, so that's fine, right? Because all the characters are small numbers. Okay? Here I'm taking a 1 byte quantity, turning into a 3 byte quantity, so what's going to happen? The other 3 bytes will be 0. The negative number, actually, the 3 bytes will be all F's. Okay? And then here, I'm actually converting format. I'm converting format of an integer, which is in one format, to a float, which is in another. I might lose information on this, right? Because ints, if I 2 to the 31 minus 1 is an int that you can't represent in this floating point number, because it just has, the mantissa has too much stuff in it. Okay? Now, with the compiler, with these are kind of natural type shifts, so the compiler doesn't tell you about them, right? But when you do them, it works. So if I compile this, I think I've already said make. All right, there you go. C's 97, I's 97, F's 97, but we did typecast with all of those. And the compiler didn't yell at me for that. Well, let me see if I can prove that. Yep, it didn't yell. Okay. Now, there are times where this might be an issue. Oh, please. I'm bad teaching today. All right, let's say I say C equals, well here, let's just say C equals 5,000. What if my compiler would yell at me on that one? That's just a warning, who cares, right? But when I do this, right, it runs and it works, and what happens? When I set C to 5,000, it gets set to negative 120. Why? Because I've done this typecasting, right? And normally, so the compiler likes to warn you when you're doing something, when you're doing the typecast that the compiler says might be dangerous, some compilers will warn you about it. It's always kind of good to heed that warning. Okay, now, if we go back to this one here, the compiler warned us on that one. Right, you'll notice it warned us, A, that this didn't match that. So this said, I'm expecting, so the 0x is just going to print out 0x. %LX says it's going to be a long, right? So 4 or 8 bytes depending on my machine. And print it in hex. That's what this is saying, lowercase hex. And so this, my compiler says, well, this is a pointer. So I don't think you know what you're doing. And so what you need to do in this circumstance is you do a typecast. So if you say unsigned long here, and unsigned long here, what the typecast is doing is telling the compiler, I know what I'm doing. That's what that says, is I know you're worried about me, but it's good. I know what I'm doing. Trust me. Now, whether or not you're correct in that is, of course, up to you. But now when I do it, the compiler warning goes away, but still runs the same way. It's interesting. No, it is different. That's one of those weird things. You'll note these numbers are different. You got to look in the middle here. They're different. You know why? Security is the people who wrote the tools. This is the loader, actually. I'm not like the compiler, but have decided that if you always get the same addresses and we don't zero out the memory in between, and I've loaded the same process in the same place, you're going to see the same memory, and maybe that's a security violation. There are all sorts of security violations of you. When you start up your program, if your operating system doesn't zero out the memory, which most of them don't, they don't zero out the memory when you load or when you exit, it means you can look at what was there as a big source of security bugs. Okay. I mean, just imagine you got credit card software that you knew was running. Okay, well, let me look at the bytes. All right, so that's one attempt of making that more difficult. I don't like it because I'd like it to be the same because I like to be able to reason about it. Yes, sir.
Can you explain real quick how the 5,000 turned into negative 120?
Yeah, absolutely. Absolutely. Let's do that with %x. Let's do this with %x. And here, let's also do 5,000 %x. There we go. C equals that. So we'll do C again, and we'll do I again. Okay. Yep. Okay. I didn't put the 0x in front of it. Here's 5,000 as hex. Or are you right there? Okay. As hex, 5 is 1388. Okay. You'll note C, what it did was when I set C to 5,000, it actually took these 2 bytes and made them go away. And since the top bit of 8 is a 1, it said, oh, it's a negative number. So it turned all the bits to, well, actually the C itself is a char, so it actually doesn't have these F's. It just has that. I'm printing as an int, so it's extrapolated out. But C is just 88. So now when I set I to C, which is just 88, then it takes it and it needs to fill in those extra 3 bytes, and it fills them in with 1s because that bit was set. So that's why you get negative 120.
What if you made the C into an unsigned char? Does that even exist?
It's a great question. No, it does exist, and the exact same thing's going to happen. Is it? I don't know. Let's watch. Let's call it an unsigned char. I like you all asking questions. Thank you. I appreciate that. All right, so now C is an unsigned char, so now it's going to treat it as a number between 0 and 255, so that now it ignores the signed bit, but now it goes up. It's bigger than 128. It's still 88, but now we don't get the F's because I'm printing it as an unsigned int, and so now since it's an unsigned int, it doesn't do that. Boy, this is a tough example. That's why I shouldn't go off book. Okay, but you can see it's still 88. Okay, good question. Real good question. It's confusing. I'm just going to tell you right now. If you're confused about that, I don't blame you, right? Then when I said printf %x C, %x, there actually is a typecast there. %x prints out an int. And so what it did was it turned C into the int. God, it's onside int. It's a tough example. Those of you watching the video, don't spend too much time on that. It's hard. Okay. All right. Old school stuff, but it's also a temptation. So I need to go over the temptation to you. What on earth is my program? I should have it in my notes. There it is. P8. Okay. Now let's go over this program here. It's always best for me to just delete these comments because then you read the comments and you have no idea what's going on. I can comment myself. All right, so what we do is I got a character array of 4 characters, S, okay? I go ahead and I stuff Jim into it. I'll go through stir copy, but what that does is that's going to take the string Jim and copy it to those 4 bytes. I need 4 bytes because it's got the null character, okay? Then I do this typecast. And in doing this typecast, you'll note I tell the compiler, I know what I'm doing. Okay? Why is this a dangerous thing? Because this is an 8-byte pointer, and that's a 4-byte integer. So it's taking 8 bytes and stuffing it into 4. You might lose information. You might not. It depends on the pointer. Okay? And now I print stuff out. Okay? So I go ahead and I print out I, and I print out S. And I print them in decimal and in hex. Okay? Then I increment I, and I stuff it back into a char star. Okay? So now I'm taking a 4-byte quantity, putting it into an 8-byte quantity. What's going to happen? Well, it's going to fill in those extra bytes either with zeros or Fs, right, depending on the sign bit of I. Print it out. Now I print out, after incrementing it, and then I print out their values, S and I and S2, and then I print out the first bytes of S. What do I print S, stuff this back. I print the first byte of S, the second byte of S, and then I print star S2, which is the first byte of S2. Okay. Now, if everything was 4 bytes, this program, all it would do is set S2 to be S1 plus 1. It would just be pointing to the second byte, I. Okay? But since pointers are 8 bytes and integers are 4 bytes, there's a chance if those high order bytes of S are set to something besides 0, then I'm going to lose information here. I'm going to lose information here. And what am I going to get here? I don't know. So let's watch. First off, do we get compiler errors? Yeah, look at that. This is a chatty compiler. Right? Compiler says, even though you did a typecast, I still don't think you know what you're doing. Right? Which is good, because what I'm doing is wrong. Okay, so if I run it, what do I get? Okay, here's S. You'll note the upper 4 bytes of S have information, right? Because each hex digit is a byte. So 1, 2, 3, 4, 5, 6, 7, 8. They're the low 4, right? They're the high 4, but those 2 are set. So when I typecast this to I, you'll notice I've lost those because I only has 4 bytes. But the bottom part of the hex matches. Okay? Worse yet, since the top bit is set, B, when I turn it back to S2, it sets all those bits to F because it thinks it's a negative number because that top bit B is set. And so now, when I try to print the stuff out, I get a segfault. Okay? So that's what's going on in this program. And I do this because sometimes you're going to be tempted. Okay? Sometime in this class, you will be tempted to stuff a pointer into an int because you want to manipulate the int and you don't want to manipulate the pointer. And then you might have this problem. Okay? Now, if you're on a 32-bit machine, I'll get you. Just a sec. If you're on a 32-bit machine, this code's going to work fine. In fact, on a Pi, you don't even get a compilation warning. It's like we're all good, and it works just fine. If I turn the ints to longs, right? So long. I mean, I'm going to get some printing errors here, but that's okay. Yeah, so I got some formatting things, but it should work. Yeah. Now if I turn them into longs, since longs and pointers are guaranteed to be the same size, now, boy, it sure feels like I've lost information, doesn't it? Oh, because I printed it as an int. I need to print it as a long. If I print it as a long, you'll see it has the whole thing in it, right? But I haven't lost information with I. Here, let me do that because that's confusing. All right, so here, let's print it out as a long. Right, so I didn't do LX. Well, at least it's showing those bits. So now I hasn't lost any information, so now S2 hasn't lost any information. And you see, S0 is going to be the J, S1 is the I, S2 is 1 byte beyond, so it's I. Okay, cool.
Why is the address for S, it's only like 6 bytes? Is that because like there's leading zeros or?
This one here?
Yeah.
Yeah, the leading zeros. I didn't, if you want to see them all, because I just did %X, right? So here I could have done, right, so here's 0, 1, 6, and that means right? There it is down there with the 0, 1, 6. That one says 16 digits, leading zeros, please print them. Okay. So, good stuff to know. This is all stuff that's going to be on your Lab 0 test. Some of that's going to be in your Lab 0 test, so it's good for you to see all of that. Okay, other questions about this? Okay. All right, malloc and free. So in C++, we had new. What does new do? New gets memory. It gives it to you in a pointer, and now that's my memory, and I can use it until either my program goes away or I delete it, right? C doesn't have new. C has malloc. Malloc, like everything in C, is more difficult to use. With malloc, here we'll say man malloc and see what garbage my Mac gives me. Because morons write stuff. Oh, that's not that bad. Okay, I'm good. There's malloc, okay? So with malloc, you just give it a size. You say, hey, I want this many bytes. The runtime system and the operating system don't give a crap what you're doing with these bytes. They just say, okay, here you go. So if you allocate 4 bytes and then you use it as a long, that's on you. That's not on this, right? Whereas in C++, you say new and then you give it it has a type specification in there. It knows how you're using it. You can still misuse it, but it makes it harder. So with malloc, A, you just give it the size, and then B, it doesn't have any clue what you're doing with it. It doesn't know how big it is. Well, that's not true. Now, free is the equivalent of delete. Right? Now, with delete, you're giving it back, right? Either because you want to save memory or because you're going to reuse memory and so you don't want to waste it. Okay? Free just takes a pointer. You'll note there's no size in there. So how does free know how big the size is? Well, stay tuned because you're going to write malloc. Okay? But the key is that free knows the size if it's a pointer that was returned from malloc. If it was not returned from malloc, free has no idea what the size is. And guess what? It's just going to guess. And those are the worst bugs in the world, are where free has made a mistake. Okay? So when you call free, you've got to call it on something you malloced. Okay. I mean, it's the same with delete, right? Delete, you have to call it on what you return new, but with delete, it's harder for you to make a mistake, whereas malloc and free, they do not care. Malloc returns a void star. It's a pointer. It doesn't know the reason it's a void star. It doesn't know what it's pointing to. That's for you to decide. So that's what a void star is. It's just a pointer. All pointers are the same size, so typecasting from one pointer to another, fair game. Dangerous? Sure. But fair game. So what you do when you return from malloc, what I do is I typecast it to the type I want. Okay? So let's do an example. Okay, so here is a procedure. Here, let's get rid of that. Get rid of that. You don't care about comments. All right. What's going on? We'll start in main. Okay, so main, you give it a size. Okay, it's going to yell at you if you don't give it a size. It's going to use A to I to convert that string to a size. A to I is bad. Just telling you right now, A to I is bad. If you're doing an interview and you use A to I, expect that you're going to be judged poorly on it, unless you give a caveat. And what's the caveat with A to I? Well, if 0 is legal, then okay, maybe A to I is okay. Actually, if 0 is illegal, A to I is better, because A to I returns 0 when it fails. So if you give it Fred, it returns 0. That's why you get dinged on the question. If you really want to convert this to an integer, you should use something else, like scanf. That's in C, you'd use scanf. In C++, you use a string stream. Right? Is there a better way than a string stream?
Oh, in C++,
Yeah.
you use like format, but I was going to say in this, you also, in like C11, I think they introduced string to str.
Oh, and it has good failure semantics?
Yeah, it sets there or no.
There you go. Oh, it sets there, no. Okay. Yeah, I wouldn't use it still.
But still, but
'Cause
that's
I'm old.
actually what this.
Well, I would use it just because I like to use the oldest possible thing I can so that my code is as portable as it can be. And scanf gives me what I want, even though that's more convenient. And it may well be someday the compiler's going to make scanf illegal. Right? Compilers, we'll go over it. Compilers now I'll go over want to go over sprintf. Compilers, there are compilers now that will yell at you if you use sprintf, and that sucks. And I understand, so I've stopped because I like my code to compile. All right. Anyway, this is a class. That's why I don't care, right? If you give it 0, fine. Get your segfault. I don't care. So anyway, so it's taking like argument turned into a number. Then I'm calling. Give me some ints. It's going to return me an int star. Okay. Has to call malloc. If it didn't call malloc, whatever it was giving me couldn't really be a legal address, right? So it's going to call malloc to allocate an array of integers, and the array is going to have that many integers, and then I'm going to call this to fill it in with random numbers, and then I'm going to print them out. Okay. So now let's look at give me some ints up there. Right now, it's returning an int star. Okay. I call malloc, and when I call malloc, I take the return value and I cast it to an int star because malloc gives me a void star. There are some compilers that don't care. There's some compilers that will not emit a warning here because they'll be like, it's a void star to int star. You know what you're doing. But some compilers won't, so I always do it. Okay? And then I have to say, give me, I call size of to say how big is my data type, how big is it, even though I know it's 4, right? And if someone changed int to something besides 4, the world would end. Although I guess it's 2 on Arduino. So you call that tells you how big your data type is. And then you multiply it by how many items you want, and that's how you allocate that many to that item. Malloc does return null if it fails. Why is it going to fail? I don't know. You give it a negative number. It's run out of memory. The world's ended. Right? Most people don't. I'm just saying. Most people don't check the return value of malloc. I'm bad. I don't do it unless I'm writing production code. Okay. Okay. And then it returns that address. Right, and then again, key about malloc is that everything else goes away, right? P goes away, I goes away when this procedure ends, but the pointer that you're returning doesn't go away. That memory that I call a malloc doesn't go away, and that's why it's there. And I just say P goes away, it does go away, right? This pointer now is going to be assigned as a return value, and then it gets put into that, right? So 8 bytes for P for a pointer, 8 bytes for array for as another pointer, and then I set that pointer. So I'm just copying. Here I'm allocating 40 bytes, or however many bytes. In the return, I'm copying 8 bytes back. And I know I'm going slow with this, but I have to be precise. And it's good for you to think precisely on this, okay? And previously, in your computer science life, you were not required to think precisely about this stuff because it doesn't really matter, okay? This is the class where it matters. Then, okay, I call this guy with the pointer. It's going to copy those 8 bytes into that local variable. So now A has gotten copied from array. That's 8 bytes, but it's the pointer. Okay, I have to give it the size. Unlike C++, I don't know what the size is. So I have to keep track of it myself. Is that unfortunate? Yes, it is. C++ is better, no doubt. Okay, so I have to do that, and then I go ahead and it's going to fill it in. And again, I do this partially to say, right, the bytes are there. It's just an 8-byte pointer. Now I'm filling it in. LRM48, horrible. Don't ever use it. Never, ever. It's the worst random number generator in the world. Like, it puts out pattern numbers. I kid you not. Why do I do it? Well, it's portable in this class, so I don't care. Okay, but if you're doing random numbers, use a better random number generator than that one. Okay, and then I print it out. It's always going to print out the same numbers too. Why? Because I haven't seeded the random number generator. So here, make it. Let's run it. PM with, let's say, 10. Here we go. 10 random numbers. Again, it called malloc 40 and did that. If I call it again, same random numbers. God, it didn't see the random number generator. All right, that's pointers. Now, that's enough for you to do lab 1. Okay? Because lab 1 is basically a C++ lab where all you need to do is allocate a data structure. You use malloc to do that. Okay. You have to keep track of a pointer or two. But I hold your hand. Okay. Not a bad time for a clicker question. Let's do it. Those of you who are new to me, I just do this to take attendance, so I don't grade this. This is not graded. This is just to take attendance. When you give me nonsensical answers, I know you're skipping class. It happens. It disappoints me, but